In this video, we're going to talk about colligative properties. So we're going to continue our discussion of the properties of solutions, and specifically we're going to focus on 4 properties that can be defined as colligative properties. So colligative properties are properties that depend on how much solute is dissolved, not the specific identity of the solute. So it doesn't really matter how much what solute we put into our solvent. It just matters how much we put into the solvent. And the 4 colligative properties that we're going to talk about are vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. So we're actually going to talk about these first 3 in this video. And then we're going to talk about osmotic pressure in the next video. So we'll focus on these top 3 here. So let's go ahead and jump into vapor pressure and talk about how we can lower vapor pressure. So if we put a non-volatile solute, a non-volatile solute is something that doesn't produce a lot of vapor, or doesn't produce any vapor really. If we put a non-volatile solute into a solvent, it lowers the vapor pressure of that solvent. So a non-volatile solute does not produce vapor. So most or a lot of solvents or a lot of liquids produce a certain amount of vapor. So if you think about things like water, if it's in a closed container, there's a certain amount of water vapor directly above the water. We don't see it, but we know that it's there because we've talked about the equilibrium between those two things, between the water vapor and the liquid. Some liquids are highly volatile. So if you think about something like ethanol or acetone, those you typically will, especially acetone, you will notice the vapor of if there's enough of it, and those typically will evaporate fairly quickly. There are other liquids that do not produce hardly any vapor. So if we put one of those that does not produce very much vapor into something that does produce vapor, it lowers the vapor pressure of the solvent. What happens is that it keeps the solvent molecules from escaping from the liquid. So for example, if we have our pure solvent here, we notice that there are some molecules up here in the top that are in the vapor phase, and then we have all of our molecules in the bottom that are in the liquid phase. If we put a non-volatile solvent in here, then we have fewer solvent molecules up here in the vapor phase. So of course we can write an equation for this, as we can for many things. And the equation that relates to vapor pressure lowering is known as Raoult's law. So Raoult's law tells us that the observed pressure of a solution, which is represented as P with a subscript solution abbreviated here. So the observed vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent. So essentially what happens here is our non-volatile solvent dilutes the solvent. So we're going to calculate the mole fraction of solvent once we've added a solute to it, and then we multiply that times the vapor pressure of the pure solvent. So let's take a look at an example with Raoult's law. We want to calculate the expected vapor pressure at 25 degrees Celsius for a solution prepared by dissolving 158 grams of common table sugar. And table sugar is sucrose. So sucrose has a molar mass of 342.3 grams per mole. and we dissolve that sugar in 643.5 cubic centimeters of water. So we're given the density of water at 25 degrees Celsius, and we're also given the vapor pressure of water. And we want to know the expected vapor pressure for this solution. So for Raoult's law, we need the mole fraction of the solvent, and the solvent is water. So we need to know the mole fraction of water, not the mole fraction of sugar. Okay, so don't confuse those. We typically, when we've done this in the past, we calculate the mole fraction of the solute. So we'll calculate the mole fraction of sugar. But in this case, we don't care about the mole fraction of sugar because it doesn't really affect what we're trying to calculate. We know the partial pressure or the vapor pressure of our solvent. So in order to do the calculation, we need the mole fraction of solvent. So to do that, we first have to calculate how many moles we have. So we need the moles of water and the moles of sugar. And then once we have that, we can calculate the mole fraction of water. So let's go ahead and calculate how many moles of sugar we have. We have 158 grams of sugar, which is sucrose. And we're told that we have a molar mass of 342.3 grams. So if we take 158.0, divide that by 342.3, we come up with 0.4616 moles of sucrose. And then to calculate the moles of water, so we're given that we have 643.5 cubic centimeters of water. And we have to get from there to moles of water. So fortunately they give us the density, and that gives us the missing conversion factor that we need in order to get from cubic centimeters of water to grams of water. And once we get to grams of water, then we can do the molar mass of water to get moles. So we have 643.5 cubic centimeters. And for every 1 cubic centimeter of water, we have 0.9971 grams. And then if we calculate the molar mass of water, water is H2O. So if we calculate the molar mass of H2O, it comes out to 18.02 grams per 1 mole. So if we take 643.5 times 0.9971 and divide that by 18.02, we come out with 35.60 moles of water. So now we want to know the mole fraction of water. So that means that we want to take the number of moles of water and we're going to divide them by the total number of moles. So that's the number of moles of water plus the number of moles of sucrose. So we have 35.60 moles of water, and then we take the number of moles of water and we add the number of moles of sucrose. So if we take 35.60 and then we divide that by 35.60 plus 4616, we come out with 0.9872 for the mole fraction of water. So now we want to calculate the vapor pressure for the solution. So I'm actually going to have to go ahead and erase all of this. So you want to make sure that you have this part written down. And then I'm going to erase the rest of this so that I can have room to write out the rest of it. So the mole fraction of water is 0.9872. And then we're going to take the mole fraction of the water times the vapor pressure of the pure solvent. So we calculated that the mole fraction of water was 0.9872. And we multiply that by the vapor pressure of water. So if we multiply this out, we come out with 23.46 torr for the expected vapor pressure of water once we dissolve sugar in it. So we can talk about we've talked about the vapor pressure lowering. So now let's talk about what happens to boiling point when we add a non-volatile solute. If we add a non-volatile solute to a solvent, that elevates the boiling point of the solvent. So for example, you might have heard to add salt to water when you're cooking. Well, what that does is it increases the boiling point of water. So you will have to get to a higher temperature to boil your water. So how much of a boiling point elevation we have depends on the concentration of the solute. So again, it doesn't depend on what you add, it depends on how much you add. So we can calculate how much we're going to change the boiling point by taking the Malau boiling point elevation constant, which is a constant for any given substance, and multiplying that by the molality of the solute. So we have to think back to our concentrations that we've talked about. Molality is moles of solute get rid of that line there. So molality is moles of solute divided by the kilograms of solvent. So be careful when you're talking about molality. Typically, we think about things in terms of the total solution on the bottom. But for molality, we only care about the solvent on the bottom. So it's moles of solute per kilogram of solvent. If we multiply that times the allowed boiling point elevation constant, we get the change in boiling point. So let's look at an example here and see what happens to the boiling point when we add a solute. What is the boiling point of a solution made by dissolving 1.50 grams of salt and 75 grams of water if the kb for water is 0.51 degrees Celsius times kilograms divided by moles? So, if we're going to do that, the first thing we need to know is the molality of the solution. So to calculate molality of solution the molality of the solution, we need to know the number of moles of salt, and we need to know the kilograms of our solvent, which is water. So we have 1.50 grams of sodium chloride. And if you calculate the molar mass of sodium chloride, it comes out to 58.44 grams of sodium chloride per 1 mole of sodium chloride. So if we take 1.50 divided by 58.44, we come out with 0.0257 moles of sodium chloride. And then we need the kilograms of water. So we have 75 grams of water, and we know that there are 1,000 grams per kilogram. So 75 divided by 1,000 comes out to 0.075 kilograms. So we want to calculate the molality. So we take the moles of salt, moles of sodium chloride, and we divide that by the kilograms of water. And if we divide this out, we come out with 0.342 molal. So if we plug this back in, we have delta T is equal to the Kb, which is our allowed boiling point constant, times molality. So our allowed boiling point constant is 0.51 degrees Celsius times kilograms over moles. And if we multiply that by 0.342 molal, 0.51 times 0.342 gives us 0.17 degrees Celsius. So this is the change in boiling point. The question asks us, what is the boiling point of the solution? So the boiling point of water is 100 degrees Celsius. And we're going to increase the boiling point by 0.17 degrees Celsius. So we end up with a boiling point of 100.17 degrees Celsius. So we don't increase the boiling point by very much, but if we added more salt, we could increase it even more. So for example, if you look at a graph of the pure freezing point and boiling point of a solution, if we look just at the boiling point for now, if we had the boiling point just a pure water by itself, this would be our boiling point. We increase the boiling point of our solution when we add a solute. We lower the vapor pressure. So this is the vapor pressure of pure water here. This is the vapor pressure of a solution. So we lower our vapor pressure. And the last colligative property that we're going to talk about in this video is the freezing point of a solution. So we actually lower the freezing point when we add a solute. So this is the freezing point of water. This is the freezing point when we add a solution to it. So when a solute to our solvent. So we call this freezing point depression. If we add a solute to a solvent, the freezing point of the solution is lower than that of just pure water or just the pure solvent. So for example, if you have ever lived somewhere where it gets really cold and you get a lot of snow and ice, when they're expecting there to be snow or ice, they will put sand or salt on the roads. What that does is, when that mixes with water, it lowers the freezing point of the water. So when you mix salt or sand in with the freezing rain or the snow as it's coming down, it lowers the freezing point, and so you don't get as much of it on the road. You don't get as much snow and ice on the road, and what does get on the road will melt, so that you end up with less snow and ice on the roads that you're trying to drive on. So water, if you take water in solution, that has a lower vapor pressure than that of just pure water or pure ice. So as we cool the solution, eventually we get to a point where the vapor pressure of ice and that of liquid water are equal. And at that point, the temperature is well below 0 degrees Celsius. So we've lowered the freezing point. So just like for our boiling point elevation, we can also write an equation for freezing point depression. And the equation for freezing point depression is actually very similar. We take the molality freezing point constant instead of the boiling point constant and multiply that by the molality of the solution. So we want to know what is the freezing point of a solution made by dissolving 1.50 grams of salt and 75 grams of water if Kf for water is 1.86 kilogram degrees Celsius times kilograms times mole. So we actually already calculated the molality of this solution because this is the exact same solution we had in our last example. We have 1.50 grams of salt and 75 grams of water. So if we take our equation here, the change in the freezing point is equal to the constant times the molality, and our constant is given to us as 1.86 degrees Celsius times kilogram per mole. And we calculated that the molality of this solution was 0.342 molal. So if we take 1.86 times 0.342, we have 0.637 degrees Celsius. And we want to know the freezing point of the solution. Well, the freezing point of pure water is 0 degrees Celsius. And this lowers the freezing point. So we would now have a freezing point of 0.637 degrees Celsius. So we will get some more practice with these calculations in class, and we will talk about osmosis in the next video. So I will see you in class.